I'm just going to take a second to try and fix this offset thing, which is not ideal. And while I'm doing this, I'm also going to attempt to simultaneously advertise the Journal of Mathematics and Arts, which is, it's a journal that's like 8 years old or so. And since we're doing a while, if you're doing things which involve mathematics and some form of the arts, for example, sculpture or anything like that, then please consider it as a venue to publish your work. There's also things like the use of artwork or sculpture in education. So come and have a talk to me about that if it's something you might be interested in. So yeah, let me just try and fix this. Oh my gosh. There's no buttons to press. I guess I'm just going to go with it. So, well, maybe I can just, if I just do that, maybe that's good enough. Yeah, maybe I'll just do that. Okay, so rather than the full screen experience, which is still cut off at the side, we'll just do this. And actually, let me also quit the thing that makes the screen dimmer as it gets later at night. Perfect. Okay, great. So let's actually begin. Okay, so I'm going to try and tell you how to make sculptures of four-dimensional things. Before saying anything else, I guess I should say something about what is four-dimensional space and how are we going to try to make sculptures inside of it. How do you think about points in three-dimensional space? How do you describe something in three dimensions? You write down three numbers, which tell you sort of how far along in one direction and how far along in another direction, and how far up you move, and then that specifies some points in that space. You need to set up your three axes at right angles, and then off you go. You can describe points in space with three numbers. And so if we're going to go to four numbers, then we just add an extra direction, which is at right angles to the previous three. And we want to add an extra number that tells us how far to move along in that fourth direction. And I've run out of letters at the end of the alphabet, but that's okay, because I can steal one from earlier in the alphabet. So I can have four numbers, W, X, Y, and Z, which tell me where a point in space is. So I need to have a fourth direction to move in, which is a little tricky to figure out where it might go, unless you've already thought about these things a lot. And you may say, well, you know, this picture is clearly false, right? This is a lie. There's no way you can put a fourth direction which is at right angles to the other three. And, well, let me remind you, this is also a lie. These three lines are not at right angles to each other. Even though I made this little right angle symbol here, those are not at right angles to each other. What I've done is I've cheated. I've put some thing which maybe exists in three-dimensional space, and then I projected it flat onto this two-dimensional screen, and you were fine when it was like this. So you should be fine when it's like this. What's the difference? I just one more dimension to squish them down. I'm not doing anything fishy at all. So we have four-dimensional things, or at least we can talk about them just by writing down the coordinates of things that happen to have four numbers rather than three. So before sort of going on, let's have an example of an objective four-dimensional space that we can think about, and we can think about how to make a sculpture of. So I'm going to build a hypercube, a sort of four-dimensional version of a cube. So I'm going to start very simple with a point. I'm going to take a copy of that point, move it off to the side, and draw a line between them, and I get myself a line segment. And I can do this again. So I've got a line segment, and I take a copy of it, I move it off to the side. I move it off to the side, well, I have to be a little bit careful about how I move it. I want to move it in a way which is perpendicular to the sort of line that my line segment is already in. But I can do that, and then I can connect up the corners, and I make myself a square. And then I can do this again. And again, here's this cheating, right? This is really a two-dimensional screen. I don't have anywhere I can make a copy and shift it off from the plane that contains the square at right angles, but let's pretend that I could. And then I join up the edges and I make a cube, and then I just do it again. take this cube, make a copy, shift it off to the side, at right angles to the three-dimensional space that the cube was in already, connect up the corners, and then I've got a hypercube. So in a sense, this is a picture of a hypercube. And you could keep going, make a 5-dimensional hypercube by just doing the same thing again, and a 6-dimensional hypercube, and so on. And this is, I guess it's an okay picture in some ways. It tells you, for instance, how many vertices does this thing have, how many edges does this thing have. But in another sense, this is not a very useful picture. Somehow it's not really telling us much about the symmetry of the thing or the geometry of the thing. So okay, how do we actually see things in 4-dimensional space? And the answer is, unfortunately, we can't. It's not possible. There are people who claim that they can actually see 4-dimensional things, but I think they're lying. I don't think they can actually do it. What we can really do is, we can use our brains, which have evolved over millennia, millions of years, to understand 3-dimensional space. And we can look at sort of 3-dimensional shadows or 3-dimensional slices of 4-dimensional things. So that's pretty much what we're going to be doing, is looking at 3-dimensional shadows of 4-dimensional things in space. So, so there's a good way to sort of start getting a handle on this, is to take everything down 1 dimension, where we can understand what's going on in 3 dimensions, and we can understand what's going on in 2 dimensions, and then we can see from one to the other. Okay, we can sort of imagine how you put everything up 1 dimension as well. Would it be possible to turn off the main lights? So I'm going to be doing a lot of things with shadows. Are there light switches somewhere? At the podium? Oh, wow.
Up on the top there, those sliders.
Oh wow. Nice. Yeah, all things. Yes. Okay, that's cool. Great. Yeah, you can still see.
Oh, right.
Okay, so I will, let's actually do this as well. So I have a flashlight here, and I have a cube here. Actually, let me take this like this. So what's on this picture? It's not going to be so easy to see. Here. It's a little bit easier. So I've got a cube here, and I'm casting a shadow of that cube onto the wall. And so that's what's on this picture here. And the idea that we're supposed to imagine is you imagine you have a 2-dimensional friend who lives on the table here, or lives in the wall here. And you're trying to explain to your friend what this cube thing is, this 3-dimensional cube. And well, she can't see the cube because she's only 2-dimensional, but she can see a shadow of it. So she can see what this thing looks like. So there's many different ways of sort of projecting from 3 dimensions down into 2. This is called a parallel projection of the cube. And so maybe we'll start with the parallel projection of the cube, and she says, oh, that's very interesting. I can see this object here. I can maybe count that there are 8 corners, and I can see that there are these edges, and some of the edges are parallel to each other. And you say, yeah, that's right. And then she says, oh, except that these 2 edges here sort of crash into each other and go through each other. Is that right? And you say, no, you should not pay any attention to that bit. That's just some sort of distortion. That's an error that's coming to us from the way that we're projecting, the way that we're casting the shadow down. And I think you can even see it. This crossing here is coming from, I think it's this edge here is the shadow you can just see is crossing this edge here, and so that's what's going on. And so this is not ideal, right? This is not the best possible picture. Maybe we could improve this to explain to our 2-dimensional friend what's going on here. Well, okay, if you do the same thing, going from 4 dimensions down into 3 dimensions, then you get this object, which is it's a parallel projection of a hypercube. I'll hand these things around. There'll be lots of things handed around. And so this model is called Hypercube B by Bathsheba Grossman. Bathsheba Grossman is one of the real pioneers in 3D printed mathematical artwork and visualization. And so you can see the sort of same kinds of things are going on. Again, you can count all the vertices, and you can see that there are indeed 16 vertices. And you can tell your 4-dimensional friend, well, it looks like these edges are parallel. And your 4-dimensional friend says, yes, those edges are in fact parallel. And then you also say, oh, and this edge here sort of goes through this square face here, right? and they say, no, that's not really there. That's just it's a problem with this projection. So this edge here does not really go through this face here in the true four-dimensional thing. Somehow that's just a problem with this kind of projection. Okay, well, can we improve matters somehow? Well, so there are other shadows that we could try projecting. So let's have a go again. So let's see if I can recreate the same thing. So you got it. If you move your light source closer to the cube, am I getting anything like? It's a little difficult to see. So I guess I'm trying to do this one. My hands are working. Yeah, that's maybe close to the picture. Is it kind of close? Yeah. Okay, so this is not solving any problems because you still got edges crashing over each other, but it looks pretty cool. So here's an interesting thing to think about for just a minute. So the shadow on the wall looks like a perspective drawing of the cube. Right? It looks like if you were to sketch a picture, it would look like a perspective drawing. And why is that? This is sort of an interesting thing. Here's a picture that sort of explains why. So here's the light source up here, and here's the again. It's not actually a real three-dimensional picture. It never was. This lived on a computer somewhere, and maybe the computer thought it was three-dimensional, but it's not. It's just two-dimensional. But your three-dimensional brains can say, okay, yeah, that's a cube. And then here's the shadow. And what I've done is I put a little screen in front of the rays of this light source. So this is sort of the same picture of this as this, except that instead of having your screen, if you like, on the table, I just moved it up and pulled it forwards. But these lines are all in the same place. And when you do it, you get this picture here, which is a perspective picture of a cube. And now why is it that this is the same as what your eye sees when it looks at a cube in perspective? Imagine instead of this being a light source, this is your eye. And instead of the light rays going this way, they're going the other way. And then this corner here, say this cube here, hits this point of the screen here and then goes into your eye. And so your eye sees this when looking at the cube from the other direction. Does that make some sense? So that's why shadow looks the same as a perspective drawing of the cube. Okay, but anyway, this is not so helpful. As I said, these edges are crashing through each other. But instead, what you could do, and this does help, is you can put the light source in the middle of the face, and now, well, we're winning somehow. None of the edges are crashing into each other. But we hold them in the same place while turning around to talk to you. Not easy. So yeah, so if we do this, then we manage to have the edges not crash into each other. And so you say, yeah, this is better. It's still not perfect. So why do I say this isn't perfect? So yeah, it's true that in the real cube, we know that none of the edges crash through each other. And they don't crash through each other in the shadow either. But let's count the faces. Where are the 6 faces of the cube? There's one in the middle. So the bottom face of the cube is this one in the middle. And then there are 4 faces around the sides, and those have got a little bit distorted, but let's not worry about that for the moment. And they appear around here. Where's the top face of the cube? It's covering all of the other 5. So there's no edges that are crashing into each other, but the faces are crashing. So the top face of this thing covers all of the other 5. So it's, in a sense, this is still not perfect. So how are we going to fix this? Before that, right. Well, you can 3D print this as well. Sorry. So this is Hypercube A. Apparently she did things in the opposite order than I would. By Dashiva Grossman again. And this is a perspective projection of the Hypercube. So I'll have these around as well. And it has the same sort of features. You can see that there's one cube in the middle. So that's the bottom cube in the 4th dimension. which is the closest to the three-dimensional plane that we're casting shadows onto. And then around it, instead of there being 4 sort of trapezium squares, there are 6. Wait, trapezoid means something else in America. So there are 6 sort of cuboid, but whatever that shape is, these things here. There are 6 of these around here, and then there are 8 cubes. Where's the 8th one? The 8th one covers all of the other 7. But otherwise, it's pretty good. So you can easily count where are the cubes, where are the edges, and so on. So this is getting a little better. Okay, how do we get even better? Let's see if my slide prediction is correct now. Yes, it is. Okay. So to get even better, we need to use stereographic projection. So some of you were playing with this already, but if you haven't seen this, then so here's a model. It's a sphere with some sort of grid pattern drawn on it. Okay, and well, I have to sort of set it up, use it the right way. So depending on where I put the light source, I get different kinds of pictures. And if I put the light source in exactly the right place, and I step close to the wall, it's kind of big, then if I hold it in exactly the right place, I should get just a square thing. It's pretty. So what's going on here? It's turning this sort of, it's turning this weird curvy pattern. Oh, I guess I could use the floor, but nobody can see it if I did. And it's also really tricky to, don't have enough hands. Let's see. Right. Okay, so we could just do this. It might be easier. So what's happening here is I've got my light source. So this flashlight has this, you take the top off and it's just a bare LED and it's really small. So it acts like a point light source. So I've got this light source up here and it's casting shadows down onto the plane. So stereographic projection is a map from the sphere, here it is, to the plane. And the light rays show you what this map does. So a light ray comes along from the flashlight and it hits the sphere and it hits the plane. And the map is where does it hit on the sphere, maps to where does it hit on the plane. So you can see so this pattern on the sphere blocks some of the light rays. And so where it blocks them, is that right? It is that. The corner is, I don't know, 1, 2, 1. I think it's there, yeah. So this point it goes to here. So that point maps to this point. So, just while on this slide, this is not an easy picture to take. As you see, this is holding it in exactly the right place and pressing the shutter button. And what you can't see is that this is attached to a stick that's attached to a crossbar, which has like 2 clamp stands on either side. The hand is purely decorative. It does not have anything to do with where the light is at all. But you didn't know that until I told you. Okay, so here's this map, stereographic projection. How are we going to use this? So I want to show you how to get from a cube down onto the plane where our 2-dimensional friend can see it. But there's a problem because stereographic projection is a map from the sphere, not from a cube. So first of all, I have to get a cube onto a sphere. So this is a little tricky to see what's going on here. Here's my light, which is inside of the cube, and here's sort of a sphere around here. Here's a sort of schematic picture, which is easier to see. I've got my cube sort of inscribed inside of a sphere, and I'm just going to blow it up into a sort of beach ball cube. So I radially project it outwards onto the surface of the sphere, and now it's on the sphere. So then I can do stereographic projection. Again, so I've got this sort of beach ball curvy cube, and then I do stereographic projection again down onto the plane, and now this I claim is, well, this I know is my favorite projection of a cube down onto the plane. Now, you may complain, this is supposed to be an edge, like a straight edge, because it doesn't look very straight, which is a fair criticism, but I fixed all the problems with crashing and things, right? So again, you can see that the edges don't crash into each other, and now the faces don't crash either. So again, the bottom square is here, and then there are 4 squares around the outside, where's the 6th square? Where's the top square? It goes outside, right? So a light ray sort of comes along here and goes out here and then goes out here. So the entire outside of this picture is the top square. And so what's going on here is stereographic projection is it's a one-to-one map from the sphere to the plane. So that's not quite true. It's almost one-to-one because there's one point on the sphere that doesn't map onto the plane. The very North Pole itself has nowhere that it goes to. So if you could sort of imagine, if you start moving up the sphere, where do I end up on the stereographic projection? As you move nearer to the North Pole, you get further and further and further out. And the North Pole is somehow infinitely far away. Okay. So there's another view of the same thing. And if you do that for the hypercube, this is what you get. You get this sort of curvy beach ball hypercube. And again, I mean, it's not that different from the previous one, but there's certain advantages to stereographic projection, including the one that the point that sort of all 8 cubes have their own space. There's no overlap. And here's a render showing the faces of the cube as well, and you see how they bulge out. It's unfortunate. I would like to 3D print a copy of this, but it's difficult because, because we don't have sort of transparent materials that you can 3D print in yet. And so you can't, I would print this, but you just see this sort of blobby thing on the outside, and it wouldn't be very impressive. Just before I move on from stereographic projection, I want to show you a couple of other really cool things. So, actually I'm going to be talking about stereographic projection for the rest of the talk, but before I move on from these pictures. So this is the one in the bottom left. So it has this pattern of triangles on here. Let's see if I can do this with the laser pointer as well. So that's not bad. So one of the really cool properties of stereographic projection is that it preserves angles. So it's conformal as the sort of technical term. So what do I mean by that? So let's see, where's a good example? So this here, you can see that these two lines, if you like, meet at prime angles. And if you find the corresponding point on the sphere itself, there's also meet at prime angles. And that doesn't always have to be the case. I mean, if I sort of move it out of the way in some horrible way, let's see, how can I do this in a way that's convincing? I don't know. Yeah, they don't look like they're at right angles anymore because my light's in the wrong place. It's only when you're right at the very North Pole that you get this effect that all the angles are correct when you do this. So somehow it's being very, it's being really kind of as faithful as you can get in sort of translating between the sphere and the plane. Here's another example. So this is a pattern with circles, like the previous one, sort of based on the symmetries of the dodecahedron. And let's see, so there's another really cool property of this, which is that not only does it preserve angles, it also preserves circles. So this is really difficult to do, and I'm not doing it right, but this thing out here, hopefully you can see is supposed to be a circle, and it's the shadow of one of the circles that's on the sphere. So, so this is kind of neat. This is kind of weird though, because if you look at the center of this circle and you compare it with this sort of pointy pentagon, the center of the circle is not really anywhere near the center of the pentagon. So although stereographic projection knows that circles are supposed to remain circles, it doesn't know where their centers are supposed to go. It gets confused. It gets it wrong. But somehow it still knows that circles are supposed to be circles. Another sort of magical property. Okay, so that's some stuff about stereographic projection. Now, I sort of swept something under the rug as I quickly went by. I said, just do the same thing in 4 dimensions, and here's the stereographic projection of the hypercube. And there was an intermediate step there where I had to radially project my hypercube onto a sphere, and then stereographically project from there to 3-dimensional space. What is that sphere that we're talking about? So what is the sphere in 4-dimensional space? Well, what's a sphere? It's a set of points that are at some fixed distance from a center. And so in three-dimensional space, here's the ordinary sphere I've drawn. I 3D printed a sort of different pattern from the things you see before. And you can see, so what have I done? I've drawn in the equator, and I've cut it up with 2 more circles into 8 octants. And so each octant is a sort of curvy triangle. So you can think of this as an octahedron, if you're familiar with that. And so by what we were saying before, this sphere is really the same as the 2-dimensional plane plus 1 point, because you don't get the North Pole. And you can sort of see here, so on this picture here, there's 4 triangles in the northern hemisphere, and there are 4 triangles in the southern hemisphere, and obviously they're all the same. But in the projection, they look kind of different, right? These ones in the southern hemisphere, yeah, okay, they're still kind of triangles. But then the ones in the northern hemisphere are these weird things that go off infinitely far away. And so they look really different. But just look back at the sphere itself and say, okay, yeah, they're really just the same. It's just the distortion from projection that makes them look different. Okay, so that's the sphere in 3 dimensions. Now for the sphere in 4 dimensions. Well, it's the set of points that are at some distance from some central point. And it's the same as 3-dimensional space plus 1 point. So again, the usual sphere in 3-dimensional space is the same as 2-dimensional space plus a point. The sphere in 4-dimensional space is the same as 3-dimensional space plus a point. And I've done the same sort of thing over here. So there's an equator, but instead of the equator being a circle, now it's a sphere, because everything goes up 1 dimension. So here, this sphere here is the equator of the sphere in 4 dimensions. And I can't draw you this picture of what the sphere really looks like. All I can draw you is the projection. It's a sort of perennial problem. But okay, so there's an equator. It's this sphere here. Instead of there being 8 triangles, there are 16 tetrahedra. So there are 8 tetrahedra here in the southern hemisphere. And they all look kind of sensible like tetrahedra. They've got 3 triangular faces on the back, and then 1 triangular face on the front here. And there are 6 edges, sure, that's a tetrahedron. And then there are these really weird stretched out ones that go off to infinity. And again, they're all exactly the same. And if you're feeling unhappy about this, just look back here, they're all exactly the same. So there are 16 tetrahedra, and you can put them together and make the 3-dimensional, sorry, the sphere in 4-dimensional space. And if you're wondering what's going on with the background here, this red edge here sort of blows up like a trumpet and expands to fill this huge sort of face here, and the green edge fills a whole huge face here, and the blue edge down here fills a huge face down here. We're inside of this space, and outside of this space is contained inside of these red, green, and blue tubes. And so not only are all of the tetrahedra really the same, all of the vertices here are the same. So one of these tiny vertices here, 3 edges meet, and there's a red and a green and a blue edge, they meet together. And this here is where 3 edges meet, they just meet very big. So, okay, so this is what the sphere in 4-dimensional space is. Okay, so let's move on briefly from stereographic projection and talk about polytopes, regular polytopes. So the illustrations that I've been showing you, cubes, hypercubes, these are all examples of polytopes. So in 2 dimensionals, people are very familiar with these things. The 2-dimensional regular polytopes are just the regular polygons. The triangle, the square, the pentagon, and so on. And there's infinitely many of them, of course. In 3 dimensions, there are only 5 regular polyhedra, the 3-dimensional versions of these 2-dimensional things. So, let's see, I've got these here, might as well hand them around. Maybe I'll split these up a little bit. It's difficult to handle 5 different small pointy plastic objects. So there's the tetrahedron that we mentioned before. This is a nice straight line edge version of the tetrahedron rather than the curvy ones we were looking at before. There's the cube everybody's very familiar with. the octahedron, the dodecahedron, and the icosahedron. Now there's, you can sort of classify what are the different, well, what about 4 dimensions? What is there in 4 dimensions? Well, you can actually classify all of the regular polytopes that there are, and they fall into 4 nice families, plus some weird things left over. So we already saw one of the nice families, the polygons, the regular polygons. This infinite family here, in fact, all of these other 3 infinite families skip across dimensions. So all of the polygons are in all 2-dimensional. All of the other ones go up in dimensions. So this one here, we already talked about. This was the construction of the hypercube. So we said, start with a point, then you make a line segment, then you make a square, and then you make a cube, and then you make a hypercube, and then you make a 5-dimensional hypercube, and then you make a 6-dimensional hypercube, and so on and so on. And the other 2 infinite families are sort of similar. So here's the one that includes the triangle and the tetrahedron and so on. So here the rule is, instead of sort of making a copy of your thing and connecting it with the corners, here what we do is you just add 1 point that's away from the line that you started with, or from the plane you started with. So it's a little hard to see what's going on when you're in 0 dimensions. In 1 dimension, then things start changing when we get to 2 dimensions. So I've got a line segment, choose a point that's not on the line segment, that's away from the line that the line segment's on, and connect up the corners, you get a triangle. If you choose a point which is off to the side of this triangle and connect up the corners, you get a tetrahedron, and so on and so on. You do the same thing again. These pictures here are these stereographic projections of radial projections. They're a little hard to interpret. We'll come back to these. These are the 4-dimensional versions. And then, so this is I guess the triangles, or the simplices, to give the technical term. The hypercubes, these are called cross polytopes. Here what you do is you add 2 points, one either side of the line or the plane or the whatever it is that everything is in already. So the line becomes the diamond, the line segment becomes the diamond, and then you add 2 points either side of the diamond, you get an octahedron and so on. And this is something called the 16th zone. Okay, so there's these 4 infinite families, and then there are 1, 2, 3, 4, 5 weird exceptions. These are the only exceptions. This seems to happen a lot in mathematics. You're trying to classify what are these things. There's very often some nice, regular, sensible, infinite families, and then there's a small class of these sporadic, weird things. So in 3 dimensions, there's the dodecahedron, the icosahedron, we already saw those. There's the 120 cell, which I'll spend a bunch of time talking about in a little while, and the 600 cell, which has 600 tetrahedra in it, which is kind of mind-blowing. And then the 24 cell, which has no analog in any other dimension. The 24 cell really is quite a strange object. But I won't say much more about this. And again, these are these things that we've been talking about. So this is radially projected onto the sphere, and then stereographically projected into 3-dimensional space. You can see. Let's get these strange things. So, right, so there's this problem. These things are really, really big. There's 120 dodecahedron here. There's 600 tetrahedra. It's really difficult to 3D print because they get small in the middle and they're big on the outside. And so if you want to fit them in the machine, then it all gets very tricky because you've got these tiny, tiny things in the middle, and so they get too fragile to print. So instead what we do is you only print half of it. So here's half of the 120 cell. It's cut off at the equator. Remember, the equator is just an ordinary sphere. And you can see the whole thing just by sort of reflecting across that equator. Everything just matches up. So you just have to buy 2 of these, and then you have a whole 120 cell. It's a little bit fragile, so just be a little bit careful with it. Okay, so I'm going to talk about 2 projects, maybe more than 2. The first project I'm going to talk about is joint work with Saul, who will be our 3rd speaker, so he'll be speaking tomorrow. I guess this is called Puzzling the 120 cell. So we wanted to understand this 120 cell. There's a lot going on here. So just as the hypercube had sort of cubical cells, or cubical faces, if you like, the 120 cell has dodecahedral faces. So it's made by sticking together 120 dodecahedra. So it's the same sort of naming scheme. Why is it called a dodecahedron? Because dodec means 12, and hedron means faces. So the name 120 cell is, again, how many things do you need to put together to make this? You need to put together 120 dodecahedra. So how do you understand this? 120 dodecahedral cells, 720 pentagonal faces between them, 1,200 edges and 600 vertices. What's going on? So one way to understand how these things put together, how do they put together, is to look at the sort of layers of dodecahedra in this, starting with the one which is at the south pole. So again, I'm doing this sort of stereographic projection thing with a beached ball 120 cell, which I've already radially projected onto the sphere in four-dimensional space. And this is a sort of schematic picture of the sphere in four-dimensional space. Here's a light source at the North Pole. Here's one point at the South Pole. And so that's the smallest dodecahedron in this whole picture. It's here at the middle. There's a really tiny little dodecahedron. And around that dodecahedron are 12 more dodecahedra that are stuck onto the face of this one. And these are at an angle of pi/5, it turns out, away from the central dodecahedron. Hi, Saul. We're just starting to talk about algebra. Glad you can make it. So pi/5, what's going on here? Well, how do you measure distance on a sphere? You measure distance on a sphere by angle. That's a sensible way to measure distance on a sphere. And so these guys look like they're very close to it. They're at a distance of pi/5 away. And then there are 20 dodecahedra that are the next distance away, the distance of pi/3. 12 dodecahedra at an angle or a distance of 2 pi/5. And then 30 dodecahedra at an angle of pi/2. This is the equator. So an angle of pi/2, that's halfway from the South Pole to the North Pole. So we're now on the equator, and we get a sphere's worth of stuff. There are 30 dodecahedra here, which fit together at an angle of pi/2. And then this pattern repeats in the last 4 layers. Again, you get 12, and then 20, and then 12, and then one more, which is sort of sitting at the North Pole, which contains the rest of the universe. Okay, so that's one way to understand these things. Here's another way to understand how these things are arranged in the 120 cell, how the dodecahedra are arranged. So you can make a ring of dodecahedra from 10 dodecahedra. Here's what you do. You start in a dodecahedron, and you choose a face of the dodecahedron, and you walk through that face, or you fly through that face into the next dodecahedron. And then dodecahedra have this nice property that there's an opposite face to the face that you enter. So you keep going through this face and out the opposite face of this dodecahedron. You keep going. And after visiting 10 dodecahedra, there's only a finite number. You have to come back eventually. After visiting 10 dodecahedra, you come back where you start. Now, if you start sort of in a neighboring dodecahedron and you go off again, then you make another ring of 10 dodecahedra that kind of wraps around the first ring. And then you can do this again, and again, and again. And in fact, you can fit 5 rings of dodecahedra. There's 1, 2, 3, 4. And then there's this last, we call this the Death Star Trench. Down here, there's this trench where the 5th ring would go in. So let's put in the protective extra ring of dodecahedra so you can get the Death Star blown up. Anyway, so the central gray ring is surrounded by 5 others. And this is half of it, right? So there are 6 rings of 10 dodecahedra each, so that is 60 out of 120. This is half of the rings. And then you can continue with the 7th, 8th, 9th, 10th, 11th ring of dodecahedra. And as usual, we're inside of the 12th ring of dodecahedra. So obviously, we wanted to 3D print this, because that's what we do. And we wanted to print sort of, the central ring and then these 5 that are around it. And there's a problem when you're 3D printing things. We wanted these to be separate, so you could try and fit them together and see how it worked. But if you just sort of put this in a 3D printer, it's going to come out as a solid block of plastic. And in order to have sort of separate pieces that move relative to each other, you have to separate them in the printer before you start. And this turned out to be difficult. We couldn't actually fit more than 2 of these sort of outer rings around the central one. There just didn't seem to be a way to fit 3 of them in, which is a little disappointing. Where is it? Here we go. But we did it. And here we go. So, well, I don't know if you can see this, but you can fit these together. That's a way to fit them together. Oh, that's not the way I'm showing on the screen. Do I show the other one? No, I don't. Okay, so these fit together, and then you can take them apart. And there's a very interesting puzzle. How many different ways are there of fitting these together? Which maybe I'll think about. It's so hard that we had the wrong answer for months. I don't even remember. Anyway, so okay, this is nice, but we really wanted to do all 5 of them around the central one, and so we cheated. So we said, well, so the problem is that these things are linked together. And if only they weren't linked together, then we could print them separately. And then there's no problem with having them not touch each other. And so, well, we're just going to get rid of these 4 biggest ones, and now we're much happier because now these can be printed separately, and there's just no problem. It's easy to do. And so here are the 5 ribs, we call them, because they're white and gently curved and made out of dodecahedra, like ribs. And actually, let's get rid of this central ring, because we don't actually need it anymore. And so we inadvertently made a puzzle. We call this the DC30 ring puzzle, and the reason it's a puzzle is that in the bag that you get from your 3D printer manufacturer, or I guess when it comes out of your 3D printer that you have at your home or lab or whatever, you get these 5 things, and then you have to try and figure out how to fit them together again. And this is not so easy, and I encourage you to have a go sometime this weekend at making this thing fit together. And we were sort of pleasantly surprised that it holds together on its own. Should I attempt to do this in real time on stage? Well, maybe, if I can find the right pieces. That's 3 of them. Oh, no, this is already going wrong. That's the wrong kind. Here we go, okay. Maybe I should get, it's too late now to try the dot camera. Right, so I'll just try and make it in person. It's more of a dexterity challenge than a sort of where do the pieces go challenge. Okay, there we go. So it makes this nice. Where did I put my laser pointer? Here we go. Okay, there's other ways you can cut these up into pieces. So here's another way to chop it up. So we've got this sort of line of 5 dodecahedra. This goes through the one at the South Pole, and you can fit 5 shorter ribs. These only have 4 dodecahedra in them rather than 6 around these, and you can fit another 5 around this. And we call this puzzle the DC45 meteor puzzle. So these 11 pieces fit together to make these things. And so we decided on these 6 different kinds of pieces. There's this sort of spine because, I don't know, it looks like a spine, and then there's different ribs of different curvatures. And these make a really surprising amount of different things. We were kind of shocked at how much different stuff there is. So I have a puzzle for you right now. 2 of these are photographs of the same thing, seen from different directions. Which 2? It's all going to say. Any guesses? Yeah, guess over there.
The bottom left and the one right, directly to the right of it.
Nice try. Unfortunately, no. Those 2 are not the same.
2 on the bottom right.
The 2 on the bottom right. Close, but you can sort of see this has a hole through it, whereas this doesn't. Yeah.
The one top right and the one cat corner 2.
This one?
Yeah.
No, they're different as well. This is essentially impossible. There's more guesses. All right, go for it.
The bottom left and the first row, the 3rd one over.
The 3rd one. This one. No, they're different. Sorry. Yeah, go on.
Bottom right, and then the one 2 over from it.
That one.
Yeah.
Nope, they're different. Yeah. This could take a while. It's a finite number. Do you guys want to go home and sleep at some point? I'll just say, I've had one case Okay, the last one.
They both have
It's the bottom right and the kind of top row second from the left.
Nope, they're different.
Oh.
Okay, enough. I've only had one audience where one person guessed it. In fact, there are two pairs. This is the same as this, and this is the same as this. And let me prove one of those two statements to you. So this guy here is this guy here. All right? And if I just turn it like this, it's also this guy here. So if you don't believe me, you can come up and look at it. So the moral of the story is, photographs are useless. You should come up and look at all the stuff. Okay, but this is quintessence, which is, maybe I'll just briefly mention why it's called quintessence. So Plato had this interesting theory that the five platonic solids, the regular three-dimensional things, match up with the classical elements. So for example, fire is literally made of tetrahedra, because tetrahedra are spiky and hurt. And Earth is made of cubes because you can build stuff with it. And rather less, I guess, okay, water is supposedly made of icosahedra because it's sort of flow round and flow in. And what was the thing for octahedra? It was pretty weak for octahedra. But you can see there's a problem. There's only 4 classical elements, but there's definitely 5 regular polyhedra. And so his idea was, well, see, the cosmos is made of dodecahedra. That's the quintessence, the 5th element. And just like our fossils are made of dodecahedra. Okay, moving on. A different project, joint work with Weihart and my brother, Segerman, involving monkeys. So what on earth is going on here? So let me briefly review symmetry. So what is a symmetry? So a symmetry is a motion of an object that leaves it looking the same after you do the motion. So this guy here, this two-dimensional design, has 5 symmetries. So we can rotate by 1/5 of a turn, 2/5 of a turn, and so on. And we include that's rotating by 5/5 of a turn, or is the same as doing that. So there's 5 symmetries of this object. And this is one of the starts of group theory is you can combine these symmetries together, and when you do one symmetry and then another, you get some third different symmetry that maybe you didn't have before. Okay, here's another example. So how many symmetries does this have? It has 8 symmetries. So it has 4 different rotations, including the do-nothing symmetry, and it also has 4 reflections along these lines here. Okay, so that's what a symmetry is, and so what we're going to get to is a visualization of a symmetry that you haven't seen before. That's very difficult to make in 3 dimensions, but we have ways of dealing with problems with not having enough dimensions. So, okay, first of all, I have to tell you about monkey box. So if people are familiar with Weihart's work, the drawings here were done by her. So, okay, so I've got a cube. So you fold this thing up into a cube, then you get this thing, which we're going to call a monkey ball. And it's got this design on it. So it's got tail faces of this cube and 2 paw faces of this cube and 2 face faces of this cube. And they all have handedness. So this is, I guess, depending on whether it's palm forward or palm away, this is a left paw and that's a right paw. And the tongue is sticking out to the left here and to the right here. And the tail squiggles around in a question mark here or an unquestion mark here or something. And when you fold it up, you get this picture here. And it turns out this shape has no symmetry itself. There's no motion you can make of this that will leave it looking the same. And I guess let me just sort of mention, so what happens is you go from this paw face to that one. Is this the right way around? Yes, it is. Okay, so it's a right paw over here, and I do a sort of twisting motion to the left by 90 degrees to get to the paw on the other side. And it's the same with the tails and the same with the faces. Okay, so how can you fit these together so that the faces match up? And what I mean by that is when I put the 2 faces together, it should be like left paw to right paw should match up exactly like this. So what can you do? So here's one thing you can do. You can make a line of these things, right? So so there's this twisting thing, right? As you go from one side to the other, you twist by 90 degrees to the left. And so there's a paw on the back face here which matches up with this paw, and there's a paw on the back face here that matches up with this paw, and so on. So you can fit them together to make an infinite line. So we can ask, what are the symmetries of this infinite line of monkey blocks? So what could I do, the motion of this line, which after I do it, it looks the same. I could move it to the side. I could move it 4 blocks along, right? So if I move 1, 2, 3, 4 along, this guy is the same as this guy. This guy is the same as this guy. You already see that? What else can I do? There's something sort of small that I can do. You can shift and rotate. You can do like a screw motion. So I move once this way, and now I'm wondering, oh right, yes, okay. Yes, move one this way and rotate one this way. So I sort of go forward and rotate 90 degrees to the left as well. I do the screw motion, and that's a symmetry of this. Okay, what about if I twisted them around like this? So I can sort of say, well, I don't really want to deal with that move of 4 along thing. I just want to have this sort of twist motion, so I can wrap 4 of them around into a circle and make this thing. And so this ring of 4 blocks has that same symmetry: forward 1, rotate 1 to the left. So that's all, right? Well, what next? So you can try sort of, can I get off the line? Can I make a plane? And you run into a problem. So there's one in the middle here, and these are stacked properly. But then there's nothing I can put in this 4th space here, because you don't get 2 whole faces next to each other. And so you're sort of stuck. What do? If only I could sort of, it looks like these should be glued to each other, right? It looks like this face here and this face here match up nicely, and this face here and this face here match up nicely. And if only I could fit 3 cubes around an edge rather than 4, then everything would be fine. And there is a way to fit 3 cubes around an edge rather than 4. You can make a hypercube. So we've seen this before. So you can put a monkey block in each of these faces of each of these cells of the hypercube, and then everything matches up. And this is great. So 8 monkey blocks glue together to make the cells of the hypercube. So you can ask, what are the symmetries of this hypercube? So here are the 8 monkey blocks with this it's sort of exploded, so you can see how they're connected together. And you can see that there's a ring of 4 of them around here, which has the same sort of go forward 1 and click 90 degrees to the right as we did when we had only 4 blocks. And it's not only that, there's these 4 here, the 4 going down through here, the 4 going through here, the 4 going through, there's lots of these rings of 4 of them. It turns out the symmetries of this decorated hypercube are something called the 8-element quaternion group. So there are 8 symmetries of it. So when I do this sort of rotate these things around and click 1 to the right, I also need to move these up around 1 and click 1 to the left. And that corresponds to, say, K. I guess it's labeled K here. And then there are 2 rings here that are labeled J. And then there are 2, the purple rings here are labeled I. And so if you know anything about complex numbers, then you add an I to the real numbers, and I, if you multiply by itself, you get -1. So the quaternion is a similar sort of extension. Instead of just I, we have 3 different things that are imaginary, I, J, and K. And the 8-element quaternion group has all of these 8 elements. So we've got the do-nothing, there's always the do-nothing symmetry. Then there are these 3 screw motions in 3 different axes, the reverse screw motion, and then there's a sort of -1, which sends every cube to its opposite antipodal cube. And these satisfy these are the defining conditions of the quaternion. We wanted to make a sculpture which has the symmetry, a real physical thing that shows the symmetry. So what do we have? So each monkey block has no symmetry itself, other than the do-nothing symmetry. So in order to make a sculpture, what you need to do is you need to put a design into the block, which itself has no symmetry. and then put that all into the hypercube in 4-dimensional space, radially project that to the the sphere in 4-dimensional space, and then stereographically project that to 3-dimensional space, and then you get a sculpture, which in a sense has this symmetry. Well, so, okay. So first of all, before any of that, I have to decide on the design to put in the monkey block, which has no symmetry. You have to put a design with no symmetry into the cube, and it turns out there's only one choice. It must be a monkey. And I'm kind of being serious, actually. You need to have something which connects onto its 6 neighbors. And if you want something with no symmetry, I mean, you kind of might as well do something figurative, and so you need some sort of animal. I mean, I guess you could do a cat, just about. But really, it pretty much has to be a monkey. So here's our monkey. Monkeys do have bilateral symmetry. You can break that by posing your monkey appropriately. You need to put copies of this monkey into all of the other cubes. So here they are, and you'll notice that there's this sort of left-handed twist motion to get from this monkey to that monkey. And then you, as I say, view these cubes as cells of the hypercube, radially project and then stereographically project, and then it's, yeah. Why stop with the hypercube? We can also do the 24 cell with 24 monkeys. Or we can do the 120 cell. This is only showing 75 monkeys because it gets difficult to print the 120 cell. But instead, we can do the virtual version of this. So this is at monkeys.hypernom.com. You can just go there on your web browser. So here I am flying around an animated version of this sculpture. Let me see if I can sort of get up here. So unfortunately, there's no documentation at all. So, but in case you remember, it's arrow keys to sort of drive around, WASD to rotate. So you can see that here's this ring of 4 monkeys. And so every few seconds, it's doing one of those twist motions on the head-foot axis. There are 3 axes, so the IJK, the hand faces, the tail faces, and the face faces. So instead of those, we have the head-foot connection, we have the hand-foot connection, and we have the hand-tail connection. So this is the hypercube version of this. The 24-cell version has, how many is it? I think it's, yes, four rings of 6 monkeys each. Now, you may be aware that the 24-cell is self-dual, whatever that means. What it means is I can fit another 24-cell monkeys in the same space. Or I can fit something called the 48-cell, which I haven't really talked about, but it's weird, it's not quite regular. Or I can do the 120-cell. And again, it has the same, so you can see that ring of white, the lighter colored monkeys here, and then there's 12 rings of differently colored monkeys here. Here's the ring of 12 darker colored monkeys, and they go around infinity, so they get kind of scary big on the other side. Let's see if I can catch Monkey God. He's up there somewhere. Yeah, he'll come around again in a second. There he is. Okay, there's one more thing I wanted to show you before I finish. And so I guess the next slide here is the end slide here, but I'm not done yet, because I wanted to show you one other thing that, whoops, oh, it's gone very dark. One other thing that I've been working on with Flyhart and friends, which was mentioned in the introduction, which is a game called Hypernom, sort of a virtual reality game called Hypernom. Here we go, hopefully this will work. Eventually, there we go. So this is at hypernom.com. What is going on here? So we're sort of exploring this 120 cell by rotating the iPad around. And so, well, maybe I'll just briefly say that the orientations I'll say this very quickly for the people who know or care. The orientations of the iPad are elements of SO3. And as a manifold, the space SO3 is homeomorphic to RP3, which is double covered by S3. So you can travel through the space S3 by rotating the iPad around, and you're really traveling in RP3, but it's lifting to the double cover. And you'll notice as I'm moving forwards, if you rotate the iPad to the right, then you move forwards. No matter which direction you're facing, it's kind of a thing. And you twist up the cable, but let's not worry about that. But as you move forward, you eat the cells of the 120 cell. And so the game is to eat all the cells. It's sort of four-dimensional Pac-Man. As quickly as possible without destroying your iPad or your iPhone. I guess I'll just finish by mentioning this was originally designed for virtual reality headsets. And so it has the same sort of problem. How do you win? Is you have to get this to approximately near every orientation of the iPad twice, which is difficult when it's actually a virtual reality headset that's attached to your face. So it's a fun game. It's probably best played on a sofa or the floor because you need to flop around a little. That's my talk. Thank you very much. Are there any questions?
Are there any questions?
Yeah.
First place, who was the first person to write image to the 4 dimension, and did he stop there, or did he realize that there could be any number of dimensions?
So, we've looked into this, I'm sure. Who was the first? I mean, somebody first classified the 4-dimensional poison. I don't know off the top of my head.
So George Poole's daughter, was it Alicia Alcott Poole? Was one of the first people to actually do exhaustive enumerations of poison. Against that, also, I think there's generalizations of this lot.
More questions? Yeah.
Possible to 3D print a 600 cell?
Half of it, yes, for sure. I've done it. I don't have it with me. Right, so there's sort of a choice of how thick should the edges be. And you want it to be thin enough so you can see into the inside and see what's going on. But if you make it too thin, so there's a limitation on how thin you can make an edge. So, and you can scale the whole thing up or down to try and fix that. But there's a minimum thickness, like, 1 millimeter thick, 1.5 millimeters thick, for the smallest edge in the middle. And then that's going to limit, that's a minimum size for the whole thing. You want to print the whole thing, it's probably going to be at least about this big. Yeah, it gets kind of expensive and difficult. If you don't do it with this stereographic projection thing, then it's not so bad. Like if you're not sort of trying to keep it all nice and using this projection, then you can certainly do it. And people have printed these things, but I mean, it's not as good, if you ask me, as doing it with stereographic projection. So if you're willing to distort things, yes. Or if you have a really good printer, yes. But I have not done it myself. Yeah.
What software do you use?
I use Rhinoceros 3D for the sort of CAD stuff, and then we do a lot of stuff with Python as well. So all of the right. Oh yeah, come and have a play with the puzzles at some point on the weekend. All of these pieces are entirely designed by script. There's no hand stuff at all. But then a lot of the other things, it depends. A lot of them are by hand or some combination. Yeah.
What are you using to code the virtual reality?
Oh, so this is there's a library called WebVR. So this is just running on your web browser, which is running in JavaScript. It's kind of ugly. But you can make it do stuff, and it interfaces with your Oculus Rift or presumably whatever you want to use. But yeah, it's JavaScript. It's yeah.
Well, there's no more questions.
All right, let's thank Henry for a great talk. All right, thank you, everyone.